Davey Ken here, and I've got a classic physics question for you today. This one's all about travel. Now, to go short distances, you can take your car, you can take a bike, you can take a bus. But for long distance travel, there's really only two options. You have trains, which go across continents, or perhaps across the channel. And then you have airplanes. Airplanes are our go-to method of travel for long distance travel, like across the globe long. If you've ever taken a long-haul flight, though, you'll know that it takes a long time and is not very pleasant. So what if there was a better way? What if instead of going around the Earth, you could go through the Earth? Well, in order to do that, you first have to dig a tunnel. So if you dig a tunnel to the other side, you can then fall through that tunnel. One of the things we'll have to do is evacuate that tunnel of all the air. And if we do, we should eliminate the air resistance, and we can keep friction to a minimum. We can put you inside a little train car, maybe put railings on each side of the tunnel, and here's a nice little capsule with air for you to travel through this air-evacuated tunnel. Now, one of the interesting factors about this travel mode is that you don't have to power the train. The train will fall through the Earth under gravity. It'll accelerate under gravity until it reaches the middle of the Earth, and then it'll start to decelerate. So you'll speed up, and then slow down, and stop, and turn around, and you'll wind up going back again in the same way. You'll oscillate back and forth, in fact. If you don't stop the train through some sort of brake, you'll just keep oscillating like this back and forth forever, ignoring air resistance. So the question is, how effective of a mode of transport is this? What would it feel like? How long would it take? And what would it take to build such a tunnel? Well, first of all, building the tunnel is pretty much out of the question using today's technology. Using today's technology, just getting a pressurized vessel down to the bottom of the ocean is an enormous challenge. And if you have a pressurized vessel filled with pressurized air, that air is pushing out on the container and it helps support it against the inward pressure of the water around it. And that in itself is a difficult thing to build. But here we're talking about having a vacuum chamber through the center of the Earth. The pressures there are going to be unimaginable, and to maintain a total vacuum means that you're not going to have this outward pressure combating the inward pressure of all of the mass of the Earth above you. Which basically means that maintaining a vacuum tube through the center of the Earth is not going to work. So a couple of the assumptions we'll have to make here in order to make this system work. We'll make a list of assumptions. One is that we're not going to have any friction or air resistance. And the only way to do that is to build a vacuum tube through the center of the Earth, and that's not really feasible. Another thing we're going to have to ignore is the rotation of the Earth. As you fall, the Earth will continue spinning, which is going to throw you against the side of the tube. We'll also have to assume that the Earth has uniform density, which it certainly doesn't. And finally, we'll assume that the Earth is perfectly spherical, which it really isn't, although it's kind of close. Using these assumptions, we're going to try now to determine what it would feel like to fall through this tunnel and how long it would take to reach the other side. Well, because there's no normal force opposing you, because you're free to fall, you're in free fall, you don't feel your own weight. You feel weightless. You feel what's called apparent weightlessness. So for the entire journey in this train car, you're going to be floating just like the astronauts float in the space station. It'll be an uncomfortable phenomenon if you're not used to it. Meal service is going to be a real problem. Your drink is going to float around. Your meal is going to float around. And let's not get started about what it's going to be like to have to go to the bathroom on this train. It's not going to be pretty. So there's going to be real uncomfortable challenges with just going through this journey. But is it worth it? How long would it take? Well, in order to calculate how long it's going to take to reach the other side, we're going to need to know some useful things. One of them is the force of gravity. According to Newton's law of gravitation, the force of gravity is g, which is this gravitational constant, times the mass of the Earth, times your mass, divided by the radius of the Earth squared. Now we can use this to calculate the acceleration due to gravity, and all you have to do to turn this into the acceleration due to gravity is factor out your own mass, and it becomes negative g mass of the Earth on radius of the Earth squared. Another thing we'll need is the volume of a sphere, which is 4/3 pi r cubed. We'll need to do things like calculate the mass. So the mass of a sphere is equal to its density times its volume. Now because, as we said, we're oscillating back and forth, we'll need some tools for motion, for oscillation, for simple harmonic motion, for oscillations. For any simple harmonic motion, your acceleration is equal to your angular frequency squared times your displacement from your equilibrium position. That angular frequency term, that omega, can be expressed as 2 pi divided by the period of oscillation, the amount of time that it takes to go down and come back up, one period of motion. That's ultimately what we're going to want to try and find here. To calculate this time for the Earth, we'll need the radius of the Earth, which is about 6.4 times 10 to the 6th meters, and we'll need the acceleration due to gravity on the Earth's surface, which is about 9.81 meters per second squared on average. Okay, that's a lot of information. We're going to need all of that to answer this question. First off, let's start with acceleration due to gravity, because that's ultimately what's going to bring us through the Earth. So the acceleration due to gravity is negative gm on r squared. But one of the tricky things here is that r isn't necessarily going to be the radius of the Earth. R is the distance from the center of the Earth to where we are, and we'll call that x, and that's going to be a variable. X will vary from the radius of the Earth all the way down to 0, and then across again to negative radius of the Earth. Why does that matter? Well, it matters because when you're beginning to travel through the Earth, you'll find that there's a shell of Earth which is above you, which is at a higher altitude than you, and a shell of Earth which is below you, a shell which has a lower altitude than you. And in fact, it's only the shell of the Earth that's below you that pulls you towards the center. If we look at the outer shell, there's a section of it which is above you and a section of it which is below you. But the section which is above you is much closer to you than the section below you. So even though there's less mass above you than below you in this outer shell, the force due to gravity from that small section is disproportionately large, meaning that there's lots of forces pulling you down and only a few forces pulling you up, but those forces pulling you up are very strong. They're so strong, in fact, that they cancel out the entire force of gravity from the lower shell, and the only thing left remaining is the force of gravity from the inner shell. I can demonstrate this to you using a simulation. Let's take the Earth, and we'll use charge to simulate the gravitational attraction of mass. We'll throw some charges in there and let them move around to the shell on the outside edge of the Earth. And then what we'll do is we'll plot the equipotential surfaces in this system. And we'll see that the potential changes very quickly out here, so there's strong forces out here. But because there's so few lines in the center, we know that the forces are very, very weak, approaching 0 in the center. As you see with this line, which represents the field's strength, the force of the gravitational field is very strong on the outside. It's a long line. But on the inside, it's very, very short, practically 0. So what that means is that when we want to calculate the acceleration due to gravity, we need to consider the mass of the Earth and the radius of Earth within this inner shell. not the whole Earth. So that means g is going to be equal to negative gm on x squared. Right, so that's our distance from the center of the inner shell. We also need to calculate the mass of the inner shell, not the mass of the whole Earth. The mass of the inner shell is going to be the density of the Earth times the volume of the inner shell, and the volume of the inner shell is just 4/3 pi x cubed, as x is that radius of the inner shell. Rewriting this, we get 4/3 pi rho x cubed. We'll take this result and we'll plug it back into our equation for acceleration due to gravity. That's negative g times 4/3 pi rho x cubed divided by x squared. And this is the same x. What that means is that these two x's cancel with two of the three x's on top. And what we're left with is negative 4/3 pi rho g x. That's a significant result. What it means is that g is proportional to x and opposite to x. So when we look at this result, we can say two things. G is proportional to x, but also g is opposite to x. So the acceleration is proportional to the displacement from equilibrium, and it's also opposite to the displacement from equilibrium, which means that this oscillation is simple harmonic motion, which means that we can use the equation acceleration is equal to negative angular velocity squared, or angular frequency, excuse me, negative angular frequency squared times displacement. So we can take all of this, and now we no longer need to use this complicated equation. We can simplify that all to this relationship. We know that at the surface of the Earth, the acceleration due to gravity is negative 9.81 meters per second squared. And we also know that the displacement from equilibrium at the surface is the radius of the Earth, which allows us to say that negative 9.81 equals negative omega squared times the radius of the Earth. The angular frequency is what's going to give us the period of motion, so I'm going to try and solve this for the angular frequency. The angular frequency squared is 9.81 divided by the radius of the Earth. The angular frequency is then the square root of 9.81 divided by the radius of the Earth. At the same time, the angular frequency is 2 pi on t. So making that substitution, we get 2 pi on t is equal to the square root of 9.81 divided by the radius of the Earth. Solving this for the period of motion, we get that the period of motion is equal to 2 pi divided by the square root of 9.81 divided by the radius of the Earth. And the period of motion is equal to 2 pi times the square root of the radius of the Earth divided by 9.81. Radius of the Earth is 6.4 times 10 to the 6th. Divide that by 9.81, and now we know everything in this equation. We can plug it into the calculator, and we get about 5,070 seconds. Now we only want to know the time to go across, which is half that, 2,535 seconds. And we'll divide that by 60 seconds per minute to find that the time to go across the Earth, to fall through the Earth, is only 42 minutes. It's going to be a wild ride, but it'll be a quick one. Is it worth doing? I don't know. How much of a daredevil are you?